New York style time machine. I assume when you travel back in time, you end up in the same spot on Earth's surface. At least, that's how it worked in the Back to the Future movies. If so, what would it be like if you traveled back in time? Starting in Times Square, New York, 1,000 years. What about 1,000 years? 100,000 years? 1 million years? 1 billion years? What about forward in time a million years? Mark Detling, 1,000 years back. Manhattan has been continuously inhabited for the past 3,000 years, and it was first settled by humans perhaps 9,000 years ago. In the 1600s, when the Europeans arrived, this area was inhabited by the Lenape people. The Lenape people were a loose confederation of tribes who were lived in what is now Connecticut, New York, New Jersey, and Delaware. 1,000 years ago, the area was probably inhabited by a similar collection of tribes, but those inhabitants lived a half a millennium before European contact. They were as far removed from the Lenape of the 1600s as the Lenape of the 1600s are from modern day. To see what Times Square looked like before a city was there, we turned to a remarkable project called Wallachia, which grew out of a smaller project called Manhattan. The Wallachia project has produced a detailed ecological map of the landscape in New York at the time of the arrival of the Europeans. The interactive map, available online at wikipedia.org, is a fantastic snapshot of a different New York. In 1609, the island of Manhattan was part of a landscape of rolling hills, marshes, woodlands, lakes, and rivers. The Times Square of 1,000 years ago may have looked ecologically similar to the Times Square described by Wallachia. Superficially, it probably resembled the old growth forests that are still found in a few locations of the Northwest in northeastern US. However, there would be some notable differences. There would be more large animals 1,000 years ago. Today's disconnected patchwork of northeastern old growth forests is nearly free of large predators. We have some bears, few wolves and coyotes, and virtually no mountain lions. Our deer populations, on the other hand, have exploded, thanks in part to the removal of large predators. The forests of New York 1,000 years ago would be full of chestnut trees. Before a blight passed in the early 20th century, the hardwood forests of eastern North America were about 25% chestnut. Now only their stumps survive. You can still come across these stumps in New England forests today. They periodically hold new shoots, only to see them wither as the blight takes hold. Someday, before too long, the last of the stumps will die. Wolves would be common in the forests, especially as you moved inland. You might also encounter mountain lions and passenger pigeons. There's one thing that you would not see: earthworms. There were no earthworms in New England when the colonists arrived. To see the reason for the worm's absence, let's take our next step into the past. 1,000 years back, 10,000 years back. The Earth of 10,000 years ago was just emerging from a deep cold period. The ice sheets that cover New England had departed. As of 22,000 years ago, the southern edge of the ice was near Staten Island, but by 8,000 years ago, it had retreated past Yonkers. By the time of our arrival, 10,000 years ago, the ice had largely withdrawn across the present day Canadian border. The ice sheets scour the landscape down to bedrock. Over the next 1,000 years, life slowly crept back northward. Some species moved north faster than others. When Europeans arrived in New England, earthworms had not arrived yet. As the ice sheets withdrew, large chunks of ice broke off and were left behind. Iceberg, dead ahead. When these chunks melted, they were left they left behind water-filled depressions in the ground called kettle ponds. Oakland Lake, near the north end of Springfield Boulevard in Queens, is one of those kettle hole ponds. The ice sheets also dropped boulders that they'd picked up on their journey. Some of these rocks, called glacial erratics, can be found in Central Park today. Below the ice, rivers of meltwater flowed at high pressure, depositing sand and gravel as they went. These deposits, which remain as ridges as eskers, crisscross the landscape in the woods outside my home in Boston. They are responsible for a variety of odd landforms, including the world's only U-shaped riverbeds. Weird. This one flows back onto itself. Ah, McEsker. 100,000 years back. The world of 100,000 years ago might have looked a lot like our own. We live in an era of rapid pulsating glaciations, but for 10,000 years, our climate has been stable and warm. 100,000 years ago, the Earth was at the end of a similar period of climate stability. It was called the Senegon Interglacial, and it was probably supported a developed ecologically, and it probably supported a developed ecology that would look sim. It was called the Samgamon Interglacial, and it probably supported a developed ecology that would look familiar to us. The coastal geography would be totally different. Staten Island, Long Island, Nantucket, and Martha's Vineyard would all were all berms pushed up by the most recent bulldoze-like avalanche advance of ice. 100 millennia ago, different islands dotted the coast. Many of today's animals will be found in those woods. Birds, squirrels, deer, wolves, black bears, but there would be a few dramatic additions. To learn about those, we turn to the mystery of the pronghorn. The modern pronghorn, or American antelope, presents a puzzle. It's a fast runner. In fact, it's much faster than it needs to be. It can run at 55 miles per hour and sustain that speed over long distances. Yet its fastest predators, wolves and coyotes, barely break 35 miles per hour in a sprint. Why did the pronghorn evolve such speed? The answer is that in the world where the pronghorn evolved was a much more dangerous place than ours. 100,000 years ago, North American woods were home to Canis dirus, the dire wolf, Actortus, the short-faced bear, and Simalodon fatalis, or the saber-toothed cat, each of which may have been faster and deadlier than modern predators. All died out in the Quaternary extinction event, which occurred shortly after the humans colonized the first continent. If we go back a little further, we will meet another frightening predator. A million years back. A million years ago, before the most recent great episode of glaciations, the world was fairly warm. It was the middle of the Quaternary period. The great modern ice waves had begun several million years earlier, but there had been a lull in the advance and retreat of the glaciers, and the climate was relatively stable. The predators we met earlier, the fleet-footed creatures who may have preyed on the pronghorn, were joined by another terrifying carnivore, a long-limbed hyena that resembled a modern wolf. Hyenas were mainly found in Asia and Africa and Asia, but when that sea level fell, one species crossed the Bering Strait into North America. Because it was the only hyena to do so, it was given the name Chassaforte, which means the one who saw the canyon. Next, Mark's question takes us on a great leap backward in time. 1 billion years back. A billion years ago, the continental plates were pushed together into one great supercontinent. This was not the well known supercontinent Pangaea. It was Pangaea's predecessor, Rhodina. The geological record is spotty, but our best guess is that it looks something like this. In the time of Rhodina, the bedrock that now lies under Manhattan had yet to form, but the deep rocks in North America were already old. The part of the continent that is now Manhattan was probably an inland region connected to what is now Angola and South Africa. In this ancient world, there were no plants and no animals. The oceans were full of life, but it was simple single cellular life. On the surface of the water were mats of blue-green algae. These unassuming critters are the deadliest killers of life. Blue-green algae, or cyanobacteria, were the first photosynthesizers. Breathed in carbon dioxide and breathed out oxygen. Oxygen is a volatile gas. It causes iron to rust in oxidation and wood to burn in vigorous oxidation. Once cyanobacteria first appeared, the oxygen they breathed was toxic to nearly all other forms of life. The resulting extinction is called the oxygen catastrophe. After the cyanobacteria pumped through the atmosphere and water full of toxic oxygen, creatures evolved to take advantage of that gas's volatile nature to enable new biological processes. We are descendants of those first oxygen breathers. Many details of this history remains uncertain. The world of a billion years ago is difficult to reconstruct. But Mark's question now takes us into an even more uncertain domain: the future. 1 million years forward. Eventually, humans will die out. Nobody knows when, but nothing lives forever. Maybe we'll spread to the stars and last for billions or trillions of years. Maybe civilization will collapse. We'll also come to disease and famine, and the last of us will be eaten by cats. Maybe we'll all be killed by nanobots hours after you read the sentence. There's no way to know. A million years is a long time. A million years is a long time. It's several times longer than Homo sapiens has existed, and 100 times longer than we've written language. It seems reasonable to assume that however the human story plays out, in a million years it would have exited its current stage. Without us, Earth's geology would grind along. Wind and rain and blowing sands will dissolve and bury all of the artifacts of our civilization. Human caused climate change will probably delay the start of the next glaciation, but we haven't ended the cycle of ice ages. Eventually, glaciers will advance again. A million years from now, a few human artifacts will remain. Our most lasting relic will probably be the layer of plastic will have deposited across the planet. By digging up oil, processing it into durable and long-lasting polymers, and spreading it across the Earth's surface, we've left a fingerprint that can outlast everything that we do. Our plastic will become shredded and buried, and perhaps some microbes will learn how to digest it. But in all likelihood, a million years from now, an outer space layer of processed hydrocarbons, transformed fragments of our shampoo bottles and shopping bags, will serve as a chemical monument to civilization. The far future. The sun is gradually brightening. For 3 billion years, a complex system of feedback loops has kept the Earth system relatively stable as our sun has grown steadily warmer. In a billion years, those feedback loops will have given out. Our oceans, which have nourished life and kept it cool, will turn into our worst enemy. They will have boiled away in the hot sun, surrounding the planet with a thick blanket of water vapor and causing a runaway greenhouse effect. In a billion years, Earth will become a second Venus. As the planet heats up, we may lose our water entirely and acquire a rock vapor atmosphere, as the crust itself begins to boil. After several billion more years, we will be consumed by the expanding sun. The Earth will be incinerated, and many of the molecules that made up Times Square will be blasted outward by the dying sun. These dust clouds will drift through space, perhaps collapsing to form new stars and planets. If humans escape the solar system and outlive the sun, our descendants may someday live on some of those planets. Atoms from Times Square, cycled through the heart of the sun, will form our new bodies. One day, either we will all be dead or we will all be New Yorkers. 1. Also known as the Delaware. 2. Also known as Cougars. 3. Also known as Pumas. 4. Also known as Catamounts. 5. Also known as Panthers. 6. Also known as Painted Cats. 7. Although you might not see the clouds of trillions of pictures encountered by European settlers, in his book, What 1491, Charles C. Mann argues that the huge flocks seen by European settlers may have been a symptom of chaotic ecosystem perturbed by the arrival of smallpox, bluegrass, and honeybees. 8. That is the current state of Yonkers. It probably wasn't called Yonkers then, since Yonkers is a Dutch derived name for a settlement dating to the late 1600s. However, some argue that a site called Yonkers has always existed, and in fact predates the humans and Earth itself. I mean, I guess it's just me who argues that, but I'm very vocal. 9. Though with fewer billboards. 10. Well, had been. We're putting a stop to that. 11. If anyone asks, total coincidence. 12. If you do, email me. Soulmates. What if everyone actually had only one soulmate? A random person somewhere in the world? Benjamin Staffen. What a nightmare that would be. There are a lot of problems with the concept of having a single soulmate. As Tim mentioned, put in his song, If I Didn't Have You, your love is once in a million. You couldn't buy it at any price. But of the 9,900,000 other loves, statistically, some of them would be equally nice. But what if we did have one randomly assigned perfect soulmate and we couldn't be happy with anyone else? Well, assume your soulmate is chosen at birth. You don't know anything else about who they are, but after a romantic cliche, you do recognize each other the moment your eyes meet. Right away, this would raise a few questions. For starters, would your soulmates even still be alive? 100 billion or so humans have ever lived, but only 7 billion are alive right now, which gives a human condition a 93% mortality rate. If we're paired up at random, 90% of our soulmates would all be long dead. Soulmate died in 1945, 1888, 1980, 680 CE, 2051 BC, alive until 2014. 50, 5118 BCE, 1942, 1630, 63,556 BCE. That sounds horrible, but wait, it gets worse. A simple argument shows that we can't limit ourselves to past humans. We have to include an unknown number of future humans as well. See, if your soulmate is in the distant past, it also has to be possible for a soulmate to be in the distant future. After all, your soulmate is. So let's assume your soulmate lives at the same time as you. Furthermore, to keep things from getting creepy, we'll assume they're within a few years of your age. This is stricter than the standard old gate. This is stricter than the standard age gap. This is stricter than the standard age gap creepiness formula, but we'll assume a 30-year-old and a 40-year-old can be soulmates. Then the creepiness rule is violated if they accidentally meet 15 years earlier. With the same age restriction, most of us would have a pool of around half a billion potential matches. What about gender and sexual orientation, and culture and language? We could keep using demographics to try and narrow things down further, but we're drifting away from the idea of a random soulmate. In our scenario, you wouldn't know anything about who your soulmate was until you looked into their eyes. Everyone would only have one orientation towards their soulmate. The odds of running into your soulmate would be incredibly small. The number of strangers we make eye contact with each day can vary from almost none, from shut ins to small people, to many thousands, a police officer in Times Square. But let's suppose you lock eyes with an average of a few dozen new strangers each day. I'm pretty introverted, so for me that's definitely a generous estimate. If 10% of them are close to your age, that would be around 50,000 people in a lifetime. Given that you have fi- Given that you have 500 million potential soulmates, that means that you would only find true love in only one lifetime out of 10,000. Find soulmate alone forever. With the threat of dying alone looming so prominently, society can try to restructure it by enabling as much eye contact as possible. We could put together massive conveyor belts to move lines of people past each other. But if the eye contact effect works over webcam, we could just use a modified version of chat roulette. Yep, another but. But it could be my soulmate's butt. If everyone used the system for 8 hours a day, 7 days a week, and it takes you a couple of seconds to decide if someone's your soulmate, The system could, in theory, match everyone up with their soulmate in a few decades. I modeled a few simple systems to estimate how quickly people would pair off and drop out of the singles pool. If you want to try out the math for a particular setup, you might start by looking at derangement problems. In the real world, many people have trouble finding any time at all for romance. Few could devote 2 decades to it, so maybe only rich kids would be able to afford to sit around on soulmate roulette. Unfortunately, for the proverbial 1%, most of their soulmates would be found in the other 99%. If only 1% of the wealthy use the service, then 1% of that 1% would find their match through the system. 1 in 10,000. The other 99% of the 1% would have an incentive to get more people into the screen. They might sponsor charitable projects to get computers in the rest of the world, a cross between one laptop per child and OkCupid. Careers like cashier and police officer in Times Square will become high status prizes because of the eye contact potential. People would flock to cities and public gathering places to find love, just as they do now. But even if a bunch of us spent years on soulmate roulette, another bunch of us managed to hold jobs that offered constant eye contact with strangers, and the rest of us just hope for luck. Only a small minority of us is ever going to find true love. The rest of us would be out of luck. Given all the stress and pressure, some people would fake it. They'd want to join the club, so they'd get together with another lonely person and fake a soulmate encounter. They'd marry, hide their relationship problems, and struggle to present a happy face to their friends and family. A world of random soulmates would be a lonely one. Let's hope that's not what we live in. 1. XKCD dating pools. See http xkcd.com slash 341. 2. We are the 0.99%. Laser pointer. If everyone on every laser pointer, if every person on Earth aimed a laser pointer at the moon at the same time, would it change color? Peter Lipowitz. Not if we use regular laser pointers. The first thing we want to consider is that not everyone can see the moon at once. We could gather everyone in one spot, but let's just pick a time when the moon is visible to as many people as possible. Since about 75% of the world's population lives between 0 and 120 we should try this while the moon is somewhere over the Arabian Sea. We could try to illuminate it either over a new moon or a full moon. The new moon is darker, making it easier to see our lasers, but the new moon is a trickier target because it's mostly visible during the day, washing out the effect. Let's pick a quarter moon so we can compare the effects of our lasers on the light and dark sides. Here's our target. The typical red laser pointer is about 5 milliwatts, and a good one would have a tiny enough beam to hit the moon. That would be spread over a large fraction of the Earth's surface when it would be spread over a large fraction of the surface when it got there. The atmosphere would distort the beam a bit and absorb some of it, which means would absorb some of it, but most of the light would make it. Let's assume everyone has a steady enough aim to hit the moon, but no more than that, and the light spreads evenly across the surface. Half an hour after midnight at GMT time, everyone aims and presses the button. This is what happens. Well, that's disappointing. It makes sense though. Sunlight bathes the moon at a bit over a kilowatt of energy per square meter. Since the moon's cross-sectional area is about 10 to the 13 square meters, it's bathed in about 10 to the 16 watts of sunlight, 10 petawatts, or 2 megawatts per person, far outshining our 5 milliwatt laser pointers. There are varying efficiencies in each part of the system, but none of it changes that basic equation. What if we tried more power? A 1 watt laser is an extremely dangerous thing. It's not just powerful enough to blind you, it's capable of burning skin and setting things on fire. Obviously, they're not legal for consumer purchase in the US. Just kidding. You can pick one up for $300. Just do a search for 1 watt handheld laser. So suppose we spend the $2 trillion to buy 1 watt green lasers for everyone. Memo to presidential candidates. This policy would win any votes. In addition to being more powerful, Green laser light is nearer to the middle of the visible spectrum, so the eye is more sensitive to it and it appears brighter. Here's the effect. Dang. The laser pointers that we're using put out about 150 lumens of light, more than most flashlights, in a beam 5 arc minutes wide. This lights up the surface of the moon about half a lux of illumination, compared to the about 130 lux from the sun. Even if we aimed them all perfectly, it would only result in about half a dozen lux over 10% of the moon's face. By comparison, the full moon lights up the Earth's surface with about 1 lux of illumination, which means that not only would our lasers be too weak to see the Earth, but if you were standing on the moon, the laser light on the landscape would be fainter than moonlight is to us on Earth. What if we tried more power? With advances in lithium batteries and LED technology over the last 10 years, the high performance flashlight market has exploded. But it's clear that flashlights aren't going to cut it. So let's skip past all that and give everyone a night sun. You may not recognize the name, but chances are you've seen one in operation. It's a searchlight mounted on police and Coast Guard helicopters. With an output of over 50,000 lumens, it's capable of turning a patch of ground from night to day. The beam is several degrees wide, so we would want some focusing lenses to get it down to the half degree needed to hit the moon. Here's the effect. It's hard to see, but we're making progress. The beam is providing 20 lux of illumination, outshining the ambient light on the night half by a factor of 2. However, it's quite hard to see, and it certainly hasn't affected the light half. What if we tried more power? Let's swap out each night sun for an IMAX projector array, a 30,000 watt pair of water cooled lamps with a combined output of over a million lumens. Still barely visible. At the top of the Luxor Hotel in Las Vegas is the most powerful spotlight on Earth. Let's give one of them to everyone. Oh, and let's add a lens array so the entire beam is focused on the moon. Our light is definitely visible, so we've accomplished our goal. Good job, team. What if we tried more power? Well, the Department of Defense has developed megawatt lasers designed for destroying incoming missiles in mid-flight. The Boeing YAL-1 is a megawatt-class chemical oxygen iodine laser mounted on a 747. It was an infrared laser, so it wasn't directly visible, but we can imagine building a visible light laser with a similar power. Finally, we've managed to match the brightness of sunlight. We're also drawing 5 petawatts of power, which is double the world's average electricity consumption. What if we tried more power? Okay, let's mount a megawatt laser on every square meter of Asia's surface. Powering this array of 50 trillion lasers would use up all of Earth's oil reserves in approximately 2 minutes. But for those 2 minutes, the Earth's surface would look like this. The moon would shine as brightly as the mid-morning sun, and by the end of the 2 minutes, the lunar regolith would be heated to a glow. What if we tried more power? Okay, let's step even more firmly out of the realm of plausibility. The most powerful laser on Earth is the confinement beam at the National Ignition Facility, a fusion research laboratory. It's an ultraviolet laser with an output of 500 terawatts. However, it fires only in single pulses lasting a few nanoseconds, so the total energy delivered is equivalent to about a quarter cup of gasoline. Let's imagine we somehow found a way to power it and fire it continuously, gave one to everyone, and pointed them all at the moon. Unfortunately, the laser energy globe would turn the atmosphere into plasma, instantly igniting the Earth's surface and killing us all. But let's assume that the lasers somehow pass through the atmosphere without interacting. Under those circumstances, it turns out Earth would still catch fire. The reflected light from the moon would be 4,000 times brighter than the noonday sun. Moonlight would become bright enough to boil away Earth's oceans in less than a year. But forget the Earth. What happens to the moon? The laser itself would exert enough radiation pressure to accelerate the moon at least 1/10,000,000th of a g. This acceleration wouldn't be noticeable in the short term, but over the years it would add up enough to push it free from Earth orbit if radiation pressure were the only force involved. 40 megajoules of energy is enough to vaporize a kilogram of rock. Assuming moon rocks have an average density of about 3 kilograms per liter, the lasers would pump out enough energy to vaporize 4 meters of lunar bedrock per second. However, the actual lunar rock wouldn't evaporate that fast, for a reason that turns out to be very important. When a chunk of rock is evaporated, When a chunk of rock is vaporized, it doesn't just disappear. The surface layer of the moon becomes a plasma, but that plasma would still block the path of the beam. Our laser would keep pouring more and more energy into the plasma, and the plasma would keep getting hotter and hotter. These particles would bounce off of each other, slam into the surface of the moon, and eventually blast off into space at a terrific speed. This flow of material effectively turns the entire surface of the moon into a rocket engine, and a surprisingly efficient one. Using lasers to blast off surface material like this is called laser ablation, and it turns out to be a promising method for spacecraft propulsion. The moon is massive, but slowly and surely the rock plasma jet would begin to push it away from the Earth. The jet will also scour the face of the Earth clean and destroy the lasers, but we're pretending that they're invulnerable. The plasma would also be physically tear away at the lunar surface, a complicated interaction that's tricky to model. But if we make a wild guess that the particles in the plasma act at a speed of 500 kilometers per second, then it will take a few months for the moon to be pushed out of the range of our laser. It would keep most of its mass, but escape Earth's gravity and enter a lopsided orbit around the sun. Technically, our moon wouldn't become a new planet under the IAU definition of a planet. Since its new orbit would cross Earth's, it would be considered a dwarf planet like Pluto. This Earth crossing orbit would eventually lead to periodic, unpredictable orbital perpetuation. Eventually, it would either be slingshotted into the sun, ejected towards the outer space, or slammed into the one of the planets, quite possibly ours. I think we can all agree in this case we deserved it, and that, at last, would be enough power. Periodic wall of the elements. What would happen if you made a periodic table out of cube-shaped bricks, where each brick was made out of the corresponding elements? There are two people who collect elements. These collectors try to gather physical samples of the many elements of as many elements as possible into periodic table-shaped display cases. Out of the 118 elements, 30 of them, like helium, carbon, aluminum, and iron, can be bought in pure form from local retail stores. Another few dozen can be scavenged by taking things apart. You can find tiny americium samples in smoke detectors. Others can be ordered over the internet. All in all, it's possible to get about 80 of the elements, 90 if you're willing to take some risk with your health, safety, and arrest record. The rest are too radioactive or short-lived to collect for more than a few atoms at once. The rest are too radioactive or short-lived to collect more than a few atoms of them at once. But what if you did? The periodic table of elements has 7 rows. You could stack the top 2 rows without much trouble. The third row would burn you with fire. The fourth row would kill you with toxic smoke. The fifth row would do all that stuff plus give you a mild dose of radiation. The sixth row would explode violently, destroying a building in a cloud of radioactive, poisonous fire and dust. Please do not build the seventh row. We'll start from the top. The first row was simple, if boring. The cube of hydrogen would rise upward and dispense, like a balloon, without a balloon. The same goes for helium. And the second row is trickier. The lithium would immediately tarnish. The beryllium is pretty toxic, so you should handle it carefully and avoid getting any dust into the air. The oxygen and nitrogen drift around, slowly dispersing. The neon floats away. The pale yellow fluorine gas would spread across the ground. Fluorine is the most reactive, corrosive element in the periodic table. Almost any substance exposed to pure fluorine will spontaneously catch fire. I spoke to organic chemist Derek Lowe about this scenario. He said that the fluorine wouldn't react with the neon and would observe sort of an armed truce with the chlorine, but everything else, sheesh. Even with the later rows, the fluorine would cause problems as it spread, and if it came in contact with any moisture, it would form corrosive hydrofluoric acid. If you breathe even a trace amount, It would seriously damage or destroy your nose, lungs, mouth, and eventually the rest of you. You would definitely need a gas mask. Keep in mind that fluorine eats through up a lot of potential gas materials, so you want to test it out first. Have fun. On to the third row. Half of the data here is from CRC Handbook of Chemistry and Physics, and the other half is from Look Around You. The big troublemaker here is phosphorus. Pure phosphorus comes in several forms. Red phosphorus is reasonably safe to handle. White phosphorus spontaneously ignites. White phosphorus spontaneously ignites on contact with air. It burns with hot, hard to extinguish flames and is, in addition, quite poisonous. The sulfur wouldn't be a problem under normal circumstances. At worst, it would smell bad. However, our sulfur is sandwiched between burning phosphorus on the left and the fluorine and chlorine on the left. When exposed to pure fluorine gas, sulfur and many substances, catches fire. The inert argon is heavier than air, so it would just spread out and cover the ground. Don't worry about the argon, you would have bigger problems. The fire would produce all sorts of terrifying chemicals with names like sulfur hexafluoride. If you're doing this inside, you'd be choked by toxic smoke and your building might burn down. And that's only row 3. On to row 4. So this is how it all ends. How ironic. Arsenic sounds scary. The reason it sounds scary is a good one. It's toxic to it's toxic to virtually all forms of life. Sometimes this kind of panic over scary chemicals is disproportionate. There are trace amounts of natural arsenic all over our food and water, and we handle those just fine. This is not one of those times. The burning phosphorus, now joined by burning potassium, which is similarly prone to spontaneous combustion, could ignite the arsenic, similarly prone to spontaneous combustion, could ignite the arsenic, releasing large amounts of arsenic trioxide. That stuff is pretty toxic. Don't inhale. This drug would also produce hideous odors. The selenium and bromine would react vigorously, and Lowe says that burning selenium can make sulfur smell like channel. If the aluminum survived the fire, a strange thing would happen to it. The melting gallium under it would soak into the alumina, disrupting its structure and causing it to be as soft and weak as wet paper. The burning sulfur would spill into the bromine. Bromine is liquid at room temperature, a property it shares with only one other element, mercury. It's also some pretty nasty stuff. The range of toxic compounds that would be produced by this blaze is, at this point, incalculably large. However, if you did this experiment at a safe distance, you might survive. The fifth row contains something interesting. Technetium-99, our first radioactive brick. Technetium is the lowest numbered element and has no stable isotopes. The dose from the 1 liter cube of metal wouldn't be enough to be lethal in our experiment, but it's still substantial. If you spend all day wearing it as a hat or breathed it in as dust, it could definitely kill you. Technetium aside, the fifth row would be a lot like the fourth. Now on to the sixth row. No matter how careful you are, the sixth row would definitely kill you. This version of the periodic table is a little wider than you might be used to, since we're inserting the lanthanide and anthracite elements into rows 6 and 7. These elements are normally shown separately from the main table to avoid making it too wide. The sixth row of our periodic table contains several radioactive elements, including promethium, polonium, actinium, and radon. Actinium is the bad one. We don't know what actinium looks like because, as Lowe put it, that stuff just doesn't want to exist. It's so radioactive, with a half-life measured in hours, that any large piece of it would be quickly vaporized by its own heat. Chemists suspect that it has a black surface, but no one really knows. There's no material safety data sheet for actinium. If there were, it would just be the word "no" scrawled over and over in charred blood. Our cube would briefly contain more actinium than has ever been synthesized in superheated gas. The heat alone will give third-degree burns to anyone nearby, and the building would be demolished. The building would be demolished. The cloud of hot gas would rise rapidly into the sky, pouring out heat and radiation. The explosion would be just to the right size to maximize the amount of paperwork your lab would face. If the explosion were smaller, you could potentially cover it up. If it were larger, there would be no one left in the city to submit paperwork to. Dust and debris covered the acetine, polonium, and other radioactive products would rain from the cloud, rendering the downwind neighborhood completely uninhabitable. The the radiation levels would be incredibly high. Given that it takes a few hundred milliseconds to blink, you would literally get a lethal dose of radiation in the blink of an eye. You would die from what we call extremely acute radiation poisoning. That is, you would be cooked. The seventh row would be much worse. There's a whole bunch of weird elements along the bottom of the periodic table called transuranic elements. For a long time, many of them had placeholders like ununumnium, but gradually they're being assigned permanent names. There's no rush though, because many of these elements are so unstable that they can be created in only particle accelerators and don't exist for more than a few minutes. If you had 100,000 atoms of livermorium, or element 116, after a second you'd have one left, and a few hundred milliseconds later, that one would be gone too. Unfortunately for our project, the transuranic elements don't vanish quietly, they decay radioactively, and most of them decay into things that also decay. A cube of any of the highest numbered elements would decay within seconds, releasing a tremendous amount of energy. The result wouldn't be like a nuclear explosion, it would be a nuclear explosion. Unlike a fission bomb, it wouldn't be a chain reaction, just a reaction. It would all happen at once. The flood of energy would instantly turn you and the rest of the periodic table to plasma. The blast would be similar to that of a medium sized nuclear detonation, but the radioactive fallout would be much, much worse. A veritable salad of everything on the periodic table turning into everything else as fast as possible. A mushroom cloud would rise over the city. The top of the plume would reach up through the acid stratosphere, buoyed by its own heat. If you were in a populated area, the immediate casualties from the blast would be staggering, but the long term contamination from the fallout would be even worse. The fallout wouldn't be everyday radioactive fallout, it would be like a nuclear bomb that kept exploding. The debris would spread out around the world, releasing thousands of times more radioactivity than the Chernobyl disaster. Entire regions would be devastated. The cleanup would stretch on for centuries. When you're collecting things for fun, when it comes to chemical elements, you do not want to collect them all. Maybe I could destroy the world just a little. 1. Think of the elements dangerous, radioactive, short-lived Pokemon. 2. An eighth row may be added by the time you read this. And if you're reading this in the year 2038, the periodic table has 10 rows, but all mention or discussion is banned by the robot overlords. That is assuming 3. That is assuming they're in diatomic form, e.g. O2 or N2. If the cube is in the form of single atoms, they'll instantly combine, heating to thousands of degrees as they do. 4. Lowe is the author of the Great Dog Research blog In the Pipeline. 5. A property that has led to its controversial use in incendiary artillery shells. 6. Search YouTube for gallium infiltration to see how strange this is. 7. In 2006, an umbrella tip with polonium-210 was used to murder KGB officer Alexander Litvinenko. 8. Radon is the cute one. 9. You know, the stuff we all shrug off. Everybody jump. What would happen if everyone on Earth stood as close to each other as they could and jumped, everyone landing on the ground at the same instant? Thomas Bennett and many others. This is one of the most popular questions submitted through my website. It's been examined before, including by science blogs and The Straight Dope. They cover the kinematics pretty well. However, they don't tell the whole story. Let's take a closer look. At the start of the scenario, the entire Earth's population has been magically transported together into one place. The craft takes up the area of Rhode Island, but there's no reason to use the vague phrase, an area the size of Rhode Island. This is our scenario. We can be specific. They're actually in Rhode Island. At the stroke of noon, everyone jumps. As discussed elsewhere, this doesn't really affect the planet. Earth outweighs us by a factor of over 10 trillion. On average, we humans can vertically jump maybe half a meter on a good day. Even if the Earth were rigid and responded instantly, it'd be pushed down by less than an atom's width. Next, everyone falls back to the ground. Technically, this delivers a lot of energy into the Earth, but it's spread out over a large enough area that it doesn't do much than leave footprints in a lot of gardens. A slight pulse of pressure spreads throughout North American continental crust and dissipates with little effect. The sound of all those feet hitting the ground creates a loud, drawn out roar lasting many seconds. Eventually, the air grows quiet. Why did we do that? Is this Rhode Island? Seconds pass. Everyone looks around. There are a lot of uncomfortable glances. Someone coughs. I should get back to Dublin. So a cell phone comes out of a pocket. Within seconds, the rest of the world's 5 billion phones follow. All of them, even those compatible with the region's towers, are displaying some version of no signal. The cell networks have all collapsed under the unprecedented load. Outside Rhode Island, abandoned machinery begins grinding to a halt. The T.F. Green Airport in Warwick, Rhode Island handles a few thousand passengers a day. Assuming they got things organized, including sending out scouting missions to retrieve fuel, they can run at 500% capacity for years without making a dent in the crowd. The addition of all the nearby airports doesn't change the equation much, nor does the region's light rail system. Crowds climb aboard container ships in the deep water port of Providence, but stocking sufficient food and water for a long sea voyage proves a challenge. Rhode Island's 500,000 cars are commandeered. Moments later, I-95, I-195, and I-295 become the sites of the largest traffic jam in the history of the planet. Most of the cars are engulfed by the crowds, but a lucky few get out and begin wandering the abandoned road network. Some make it past New York or Boston before running out of fuel. Since electricity is probably not on at this point, rather than find a working gas pump, it's easier to just abandon the car and steal a new one. Who can stop you? All the cars are in Rhode Island. The edge of the crowd spreads outward into southern Massachusetts and Connecticut. Any two people who meet here are unlikely to have a language in common, and almost nobody knows the area. This day becomes a chaotic patchwork of coalescing and collapsing social hierarchies. Violence is common. Everyone is hungry and thirsty. Grocery stores are empty. Fresh water is hard to come by, and there's no efficient system for distributing it. Within weeks, Rhode Island is a graveyard of billions. The survivors spread out across the face of the world and struggle to build a new civilization atop the pristine ruins of the old. Our species staggers on, but our population has been greatly reduced. Earth's orbit is completely unaffected. It spins along exactly the same as it did before our species wide jump. But at least now we know. A mole of moles. What would happen if you were to gather a mole, unit of measurement, of moles, the small furry critter, in one place? Sean Rice. Things get a bit gruesome. First, some definitions. A mole is a unit. It's not a typical unit, though. It's really just a number like dozen or billion. If you have a mole of something, you have 602 sextillion, 214 quintillion, 127 quadrillion of them, usually written as 6.022 times 10 to the 23rd. It's such a big number because it's usually used for counting numbers of molecules, which there are a lot of. There are too many molecules. A mole is also a type of burrowing animal. And there are a handful of some of the moles, and some of them are truly horrifying. So, what would a mole of moles animals look like? First, let's start with the wild approximates. This is an example of what might go through my head before I even pick up a calculator when I'm just trying to get a sense of these quantities. The kind of calculation where 10, 1, and zero point 0.1 are all close enough that we can consider them equal. A mole, the animal, is small enough for me to pick up and throw. Anything I can throw weighs 1 pound. 1 pound is 1 kilogram. The number the number 602 sextillion 214 quintillion 126 quadrillion looks about twice as long as a trillion, which means it's about a trillion trillion. I happen to remember a trillion trillion kilograms is how much a planet weighs. If anyone asks, I did not tell you it was okay to do math like this. That's enough to tell us that we're talking about a pile of moles the scale of the planet. That's a pretty rough estimate, since it can be off by a factor of thousands in either direction. Let's get some better answers. An eastern mole, or Scalopus aquaticus, weighs about 75 grams, which means a mole of mole weighs about 10 to the 22 kilograms. That's a little over half the mass of our moon. It weighs about An eastern mole, Scalopus aquaticus, weighs about 75 grams, which means a mole of moles weighs 44.52 times 10 to the 22 kilograms. That's a little over half the mass of our moon. Mammals are largely water. A kilogram of water takes about a liter of volume. So if the most weighs 4.52 times 10 to the 22 kilograms, they take up about 4.52 times 10 to the 22 liters of volume. You might notice that we're ignoring the pockets of space between the moles. In a moment, you'll see why. The cube root of 4.52 times 10 to the 22 liters is 3,562 kilometers, which means we're talking about a sphere with a radius of 2,210 kilometers, or 2,213 miles on each edge. If these moles were released onto Earth's surface, they'd fill it up 80 kilometers deep, just to about the former edge of space. This smothering ocean of high pressure meat could wipe out most life on the planet, which, to Reddit's horror, threaten the integrity of the DNS system. So doing this on Earth is definitely not an option. Instead, let's gather the moles in interplanetary space. Gravitational attraction would pull them into a sphere. Meat doesn't compress very well, so it would undergo only a little bit of gravitational contraction, and we'd end up with a mole planet slightly larger than the moon. The moles would have a surface gravity of about 1/16th of Earth, similar to that of Pluto. The planet would start off uniformly lukewarm, probably a bit over room temperature, and the gravitational contraction would heat up the interior by a handful of degrees. But this is where it gets weird. The mole planet would be a giant sphere of meat. It would have a lot of latent energy. There would be enough calories in the mole planet to support Earth's population for 30 billion years. Normally, when organic matter decomposes, it releases much of that energy as heat. But throughout matter, the majority of this planet's interior, the pressure would be over 100 megapascals, which is high enough to kill all bacteria and sterilize the mole remains, leaving no microorganisms to break down the mole tissue. Closer to the surface, where the pressure would be lower, there would be another obstacle to decomposition. The interior of a mole planet would be low in oxygen. Without oxygen, the usual decomposition wouldn't happen, and the only bacteria that will be able to break down the molecules would be that don't require oxygen. While inefficient, this anaerobic decomposition can unlock quite a bit of heat. If continued unchecked, it would heat the planet to a boil, but the decomposition would be self-limiting. Few bacteria can survive at temperatures above 60 degrees Celsius, so as the temperature went up, the bacteria would die off and the decomposition would slow. Throughout the planet, the mole bodies would gradually break down into kerogen, a mash of organic matter that would, if the planet were hotter, eventually form oil. The outer surface of the planet would radiate heat into space and freeze. Because our moles form our literal fur coat, when frozen, they would insulate the interior of the planet and slow the loss of heat to space. However, the, the flow of heat in the liquid interior would be dominated by convection. Plumes of hot meat and bubbles trapped in gas, like methane, along with air from the lungs of the deceased moles, would periodically rise through the mole crust and erupt volcanically from the surface, a geyser of death blasting mole bodies free of the planet. Eventually, after centuries or millennia of turmoil, the planet would calm and cool enough that it would freeze all the way through. The deep interior would be under such high pressure that as it cooled, the water would crystallize into exotic forms of ice, such as Ice 3 and Ice 5. And eventually,